Hello everybody, and welcome to this lecture on computer architecture. Today I want to give you an example, a real-life example of a logic array or a logic circuit, a real example of something that is being done in real life, namely the multiplexer, as you can see here written above me, if I'm not mistaken. So first of all, what is a multiplexer? What does it do? And then how can we construct it with the knowledge we have until now? Remember that we were able to make any logic circuit with the functions that we had based on the Huntington postulates, Boolean algebra, and then designing sum of products, products of sums and things like this, Carnot maps, and then at the end we could implement this with circuits. So now let's look at a real-life example about how to make a multiplexer. So first of all, what is a multiplexer? Let me design here one. It is a circuit, something like this. Let me draw here a box. And then in come a number of lines, can be any number. Let's put here an example of 4. So we have input 0 until input 3. And then what we want on the output, we want that one of these inputs actually appear on the output. So we have here sort of like a switch that then connects maybe here to I2. It then connects to the input and puts it on the output. So we have, let's say in this case, we need 2 selector lines that determine which input appears on the output. So we have here out 2 inputs, 4 inputs, so we need 2 selectors because, as you know, 2 to the power 2 is 4. So if you have n selectors, you can determine deselect between 2 to the power n inputs. And one of them will appear on the output, whatever it is. If it is a 1, it will appear a 1 on the output. If this is a 0, it will appear a 0 on the output. Now, of course, this is then just any logic circuit. Here we have a logic circuit, and we can approach this with our techniques and the tools that we have learned. But this is a little bit complicated, so I will make it a little bit simpler for you to understand how it works, because we have here 4 real inputs and 2 more inputs that are the selectors. But for the logic it doesn't matter. These are just 6 input lines and 1 output line. So we have a truth table of 6 input lines, and we will have a 6-dimensional Carnot map, and we will have electronics that is quite complicated. But maybe let's make it a little bit simpler, and then you will understand how will this thing work. So let me do a simpler case. I will make here now a multiplexer, or a MUX as we call it, with 2 input lines and 1 selector. So how does this work? So what did we do? First we define the problem, then we make a truth table, then we make Carnot maps, then we simplify in the Carnot map, we simplify the function that we're going to use, the expression, and then we translate this expression into electronics and see if we can do this and can simplify it even more. So let's do exactly this. What do we have? We're going to design an electronic circuit with 2 input lines, I0 and I1, and 1 selector. So that is a logic circuit with 3 inputs and then 1 output, which we called F. So let's not be smarter than we actually are. Let's try not to be smarter than we actually are. Let's just follow the technique what we have learned. So first we construct the truth table. So we have 3 inputs. We have the selector, we have I1 and I0, and they can take any value 0 or 1. So we have all combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. 3 input lines, so we have 2 to the power 3 is 8 possibilities. So now the output, what do we want? I will put this in another color. No, this one. So if S equals 0, then we want I0 on the output. So these are these 4. Let me put it here. That is 0, 1, 0, 1. And if S is 1, then we want I1 on the output. This is these 4 here. So I want 0, 0, 1, 1. Okay, that's all very nice. So let's make a truth table out of this. A truth table, Carnot map, which we know, of course, 3-dimensional. We have 3 inputs. I'll put it like this. I'll put here on top S and not S. I will make a sum of products, my favorite. I'll make here I1 and not I1. And here I will divide this one below here also into 2. And this is I0 and not I0. You can do this any way you want, any order you want, whatever you prefer. I just do it like this to always anti-clockwise. For some reason I just do like this. So this 0, as you know, this min term that is on this line, the first line is not S, not I1 and not I0. And that will appear actually here. So this red 0 that's here appears here. If you, I will do it a little bit faster because I want to waste time on this and just look back in the other lecture that we did already. So this one that we have here actually goes to, let me see, it goes here. I already have it prepared here. So this 0 goes here. This 1 now goes here. If I do this all correct, this 0 appears here. This 0 appears, I have to look at my own notes, appears here. And then the other 2 ones that are here, they appear here and here. So now what would be the simplest expression for this? Well, we have to join the most number of ones. I see a set of ones here, which would be, let me see, not S and E0. So now the I1 has disappeared from there. And let me put this one blue here. And this one is then or it stopped for a moment for some reason, or S and I1. That's nice. So we have a very simple expression. 2 AND gates and 1 OR gate. So what is the circuit? Well, I wanted to keep this scheme like this, so I want to put the I's on the left and the S on the bottom. And I will make this circuit here. So this would be, let me undo this, otherwise you don't see what I'm doing. So we have here I1, and that is ANDed with S. That comes here from the bottom. And we have here another AND gate that is, I don't want to put it here, that is I0, but now not S. So we have here S at the bottom. And these ones are then going into our sum of products, so they are ORed. So this is an OR gate and this is an AND gate, which we use this dot, and we have here out. So what do you see now? That this selector, what it is doing is that this S, and it is inverted here and not inverted here, so it will put, actually at least in one of them, it will put a 0, and only in one of them it will put a 1, this S, and then this one that has a 1 is actually the one that's being selected, because don't forget that an AND gate is 0 when it has at least 1 0. So we could call this is deactivated. So for instance, if I put here now as a 1 S equals 1, it means that it will put a 1 here and it will put inverted a 0 here, because 0, whatever is here we have I0, doesn't matter what is there because it is ANDed with 0, so here we have 0. And here, if the I1 is 1, there will appear 1 and 1 will appear a 1 here on the exit. And if this one is a 0, then it will be 0 and 1, so there will be appearing an I0, a 0 on the exit of this AND gate. And that is the same as it lets through I1. And this I1 now is ORed in this gate, so we get here I1 OR 0, and as we know, something OR 0 is that something? So here we have I1. Because I selected here with s equals 1, I put 1. It means that we have a path here that goes I1 appears on the exit. And the same you could do, let me erase this, all this red stuff. The same you could do if you make s equals 2, and let me put blue, s equals 0. It means this one is inverted here, it places a 1 here, and it places a 0 here. So this I1 or 0 and 0, doesn't matter what I1 is, it places a 0 here. And this one, I0, if it is 0, 0 and 1 is 0. But 1 and 1 equals 1. So this one is actually letting through I0. And now I0 or 0 actually is I0. So if we select here a 0, I0 appears in the output. If I select here a 1, if I select a 1, s equals 1, then I1 appears on the output. So this is then how multiplexer works. This is the simple one, and now we will show you a more complicated one with 4 input lines and 2 selectors, but I think you get the idea already. By the proper combination of the selector lines, you can actually select which input you want. So we have it here again. These are 3 input AND gates and 4 input OR gate. So if I, for instance, put here, let me put here 1, 0. This S1, I want it in red. This S1 appears here, not inverted. So it's here, it's a 1. And I get red. The S1 appears here as 1, and the S1 appears here as 1, and here it appears as 0, and here it appears as 0 because it's inverted. And the S0 here appears inverted, so it's 1. Here it doesn't appear inverted, so it's 0. Here it appears inverted, so it's 1. And here it doesn't appear inverted, so it's 0. Now we have here at least 1 0, so it doesn't matter what D3 is, the output will be 0, because we have at least 1 0 in the AND gate. This one actually, 1 1, so what if D2 is 0, there will appear 0 here, because 0 and 1 is 0. But if there's a 1 at D2, that means we have 1 and 1 and 1, and that is 1. So what is actually appearing on this gate is the input D2. And this one, D1, is whatever D1 is, and 0 is very 0, so this one will be 0. And D0, this gate, something D0 and 1, that is also 0. So what do we have here? At the input of the OR gate, we have 0, or D2, or 0, or 0. And that, of course, D2, or 0, or 0. And that, of course, these are all zeros. That, of course, is D2. So by selecting 1, S1 equals to 1, S0 equals to 0, we let through here the D2, and that appears here on the output. And this is a classical logic array where you have, it's called a multiplexer, because by 2 selector lines you can let through to the other side of the logic array, you can let through one of the 4 input lines. And actually, when you have n selectors, you can make 2 to the power n input selection. I can imagine that you can imagine how this works by just then selecting 2 to the power n, making 2 to the power n AND gates, and then ORing them all together into a final sum of products. So this is how a multiplexer works. I hope you enjoyed this lecture. See you in the next one.